most of the stuff that we're going to do in this section is going to be review. So, but some of it will be real. We're going to tie together all the stuff that we've learned about invertible matrices into one big theorem. So let me go ahead and start with that theorem. And we start with A is an n by n matrix. The following statements are equivalent. We'll start with A is invertible. There's a total of 12 of these, and I'm going to go through each one of them to make sure that you have a strong understanding of what exactly we're trying, of inverse matrices and how they're related to everything else we've been doing. There exists an n by n matrix C such that CA equals the identity matrix. The equation AX equals 0 has only the trivial solution. A has n pivot positions. A is row equivalent to the identity matrix. Now, the way I'm setting this up, I'm going to put a little space. I'll explain it after when I start to prove the thing why I'm doing it this way. There is an n by n matrix D such that AD equals the identity matrix. The equation AX equals B has a solution for every B in Rn. I told you there's 12 of them. I'm going to group the next two together. Number 8, the columns of a span Rn the linear transformation x to ax is onto Rn. Number 10, the columns of a are linearly independent. The linear transformation x to ax is 1 to 1. And then finally, A transpose is invertible. So what it means for all these things to be equivalent is once I've proven all these things, then any one of these can be used in place of any of these other statements when you're proving theorems. So when I'm done with this, number 8 will be no different than number 5. If 5 is true, 8 is true, and vice versa. And that'll be for all 12 of these things. So you'll see why I scheduled things the way I did. Let me first start with this chunk at the top. I'm going to copy those for the proof. And I'll copy them as I go along. I'll copy the sections I'm proving at a time. So let's copy that. All right. So what we're going to do first is I'm going to prove that 1 implies 2. So we're going to assume that A is invertible. From that, I would like to prove that we can find a matrix C such that CA equals IN. Well, this is no big deal. If A is invertible, then we can use C equal A inverse to get CA equals A inverse A, which we know is equal to the n by n identity matrix. So that takes care of that. Now we're going to move on, and I'm going to prove 2 implies 3. So now, assume there exists a matrix C such that CA equals the identity matrix. And we want to prove then number 3, which is the equation AX equals 0 has only the trivial solution. So suppose AX equals 0. What I'm going to do then is multiply both sides by C, the one that I know exists. C times AX equals C times 0, the 0 vector that is. Now any matrix times the 0 vector will be the 0 vector. On the left though, let me regroup CAX, and then CA I know is the identity matrix. And so X is the 0 vector. That means that the only solution then is the trivial solution. So we've got 2 implies 3. Now we're going to go 3 implies 4. Let's scroll back up and see what 3 is. Now I just proved 3, so I now assume the equation ax equals 0 has only the trivial solution. And we'd like to prove number 4. We would like to prove that A has n pivot positions. Then we know A has no free variables. As such, we have a pivot in every column well, since we have n columns, we have n pivot positions. All right, now we just proved 4. Let's assume that A has n pivot positions. And let's see what it is we're trying to prove. So I'm looking at number 5 now. Let's scroll back up. We want to prove that A is row equivalent to IN. Well, we're already assuming that A has n pivot positions, which of course means we have a pivot in every column. Since we cannot have more than one pivot per row, every row must have a pivot position as well. Well, how's the only way that this can happen? This means that the matrix A can thus be row reduced to something like this. Let's write, we'll have a block which will be a pivot. And then the way the pivots have to work, since you got one per row and one per column, that means they have to go down in a diagonal fashion, like so. So this has to be the 1-1 position, this has to be the 2-2 position, this has to be the n position. We have star above and that below. So that is what A looks like. Now, we can use the pivots. Remember, they're non-zero, so we can use those. We can use the pivots to eliminate the star region. All you got to do is start with this guy right here and use it to eliminate all the items above it. Then move back to n-1, and eliminate all the items above it. Continue going backwards until you get to the start. So we can use these pivots to eliminate the star to get, let's see if I can, so we can get a 0 above and below like so. Well, then we divide each row by the pivot number, or just call it by the pivot, whatever that number is. I don't want to say that. I should say pivot number. To get and zeros above and below. So all of the things that I said and did were row operations. So this implies that A is row equivalent to the identity matrix. Now the reason I grouped those 5 together is now I'm going to do this. I'm going to take number 5 and go back and prove number 1. So let me scroll back here for a minute, and I'll explain the importance of this in just a second. I'm going to come back here. Once I go and show that 5 implies 1, that means that all 5 of these things imply each other. They're all equivalent to each other, because if I wanted to, say, prove option 4, but I have option 2 available to me, well, I know that using 2, I can prove 3, and then I can prove 4. And starting at 4, I know that I can prove 5, prove 1, and then prove 2, so that I can show that 2 is the same thing, or an if and only if, with number 4. And so that works for the whole process. So by showing 5 implies 1, I will show all 5 of these things are equivalent to each other. So anyways, let's assume that A is row equivalent to IN. And what we want to do is prove that A is an invertible matrix. Then there are elementary matrices. Let's call them E1, E2, up to EP. I don't know how many it's going to take, such that, if you remember when we multiplied on the left by an elementary matrix, it made a row operation happen. So we can use the elementary row operations to get to IN. That, of course, is what we're assuming, is that A is row equivalent to IN. Well, then, there you have it. You have that A equals EP ... E1 inverse times IN. Well, the IN doesn't matter. Now remember about these elementary matrices. They were invertible. Each and every one of them was invertible. I went through the effort of showing the inverse of each and every one of these elementary matrices. And you can also, if you want, you can do this. A inverse then is equal to EP ... E1. And then you get A is an invertible matrix, because A is the product of invertible matrices. Let me throw this one here. Remember when we actually take the inverse of these things, we write it in reverse order. So let me come back to this row here. A is a matrix that is equal to a product of invertible matrices, which means that A itself is invertible. And of course, the inverse is going to be whatever the product of those was. So now, we have that 1 through 5 are equivalent. Next, we prove 1 implies 6, implies 7, implies 4. Remember that 1 and 4 are equivalent, so if I do this, it's the same as if I did 1, 6, 7, back to 1 again, because 4 and 1 are equivalent. So that's the plan here. It just so happens that proving 4 from 7 is easier than anything else that I could think of. Let me put up those 4 statements so that we can have them handy. All right, and let's go ahead and start with 1 implies 6. So we assume that A is invertible. Let D equal A inverse to get AD equal A inverse, which equals IN, and that takes care of 6. Now let's do 6 implies 7. So we're going to assume there exists a matrix D such that AD equals IN. Let B be any vector in Rn. Then we have AD equals IN. So AD times B on the right is equal to INB. Of course, INB is just B. I'll reassociate on the left. And we see that we do have a solution to the equation AX equals B. So if X equals DB, then it is a solution to AX equals B. So I've got that one. And then 7 implies 4. Now we assume that AX equals B has a solution for every B in Rn. You may recall some time ago that means this means there is a pivot in every row. This was an example that I had done not too long ago. Well, n rows, we have n rows. So we have n pivot positions. And that takes care of that. So now what we have is, now we know 1 through 7 are equivalent. Next, we prove 7 implies 8, implies 9, back to 7. This will show 7, 8, and 9 are equivalent to each other, which, since 7 is equivalent to 1 through 6, that means I'll have 1 through 9 all taken care of. So let me bring back 7, 8, and 9 so that we know what we're working with. Okay, there we have it. Let's go ahead and start. 7 implies 8. All right, now we assume AX equals B has a solution for every B in Rn. Then for any B in Rn, we have X in Rn with AX equals B. Of course, I'm just restating what we have there. But recall that AX is a linear combination of the columns of A. The way you know it is we broke it down something like this: A1 dot 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 up to AN times X1 dot 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 up to XN, and that was equal to B. And the way you broke out the left-hand side is you had X1 A1 plus dot 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 plus XN AN equals B. And you can see then that B is in the span of A1 up to AN. Since B in Rn was arbitrary, we have that Rn is a subset of the span of those columns. And now we assume the columns of A span Rn. And let's see what 9 wants us to prove. 9 says the linear transformation x to ax is onto Rn. Well, that's pretty easy to do then. So let B be in Rn, then B is in the span of those columns of A, and we can write something like, let me say, and there are x1 up to xn in R with x1 a1 plus dot 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 plus xn an equals B. And of course, I'm just going to redo or reverse what I did on the last thing. This will be A1 dot 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 up to AN times X1 dot 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 up to XN. That equals B. And we have AX equals B. So for any B in Rn, there is an X in Rn with X going to AX, which equals B. Thus, since B in Rn was arbitrary, the mapping is onto. So now we assume the mapping x goes to ax is onto Rn. Now what does 7 want us to prove? Let's come back. Come here, 7. Where you at? 7 is the equation ax equals b as a solution for every b in Rn. Let b be in Rn. Since x to ax is onto, there is an x in Rn with x goes to ax equals b. This implies that ax equals b has a solution for all b in Rn. Now we know that 1 through 9 are all equivalent. Next, we prove 3 implies 10, which implies 11, which implies 3. Since 3 is between 1 and 9, or is one of the 1 through 9, I will show that 3, 10, and 11 are all equivalent, and since 3 is equivalent to 1 through 9, this will show that 1 through 11 are all equivalent to each other. So let me bring those statements in, and then we'll go from there. All right, let's go ahead and start with 3 implies 10. Here we're going to assume ax equals 0 has only the trivial solution. And let C1 up to Cn be in R with C1A1 plus ... plus CNAN equals the 0 vector. And of course, the AIs are the columns of A. But then once you have this, you can go ahead and redo it this way. And I can go one further. But remember, an equation like this only has the trivial solution. I'll put it over here. All right, this, we only have the trivial solution. The C vector equals the 0 vector. Thus, C1 equals C2 equals ... equals Cn all equals 0, which implies the columns of A are linearly independent. Next, we'll do 10 to 11. So we assume the columns of A are linearly independent. Now, what are we trying to prove? Let's see what 11 says. We are trying to prove the linear transformation is 1 to 1. Well, suppose AX equals AY. And then I can take that to one side. AX minus AY is the 0 vector. I can factor the A out. So that A times X minus Y is the 0 vector. And then we can decompose A1 ... up to AN times X1 minus Y1 ... Xn minus Yn equals the 0 vector. Let me continue. The definition of multiplying a matrix times a vector has me do this. X1 minus Y1 times A1 plus ... plus Xn minus Yn times An is all equal to the 0 vector. But the columns of A are linearly independent. That's what we're assuming right now. So X1 minus Y1 equals X2 minus Y2 equals ... equals Xn minus Yn, which equals 0. And all of this proves that X1 equals Y1, X2 equals Y2, ... Xn equals Yn. This implies then, since each of the components are equal to each other, that the vector X equals the vector Y. Therefore, the mapping X goes to AX is 1 to 1. And now we'll go back 11 to 3. Assume the linear transformation X to AX is 1 to 1. Now, suppose AX equals 0. Well, since A times 0 equals 0, we have that X equals 0 because the mapping is 1 to 1. Therefore, the equation AX equals 0 has only the trivial solution. So now 1 through 11 are all equivalent. Finally, we prove that 1 is equivalent to 12. And I know what these are. 1, A is invertible. 12, A transpose is invertible. So for that, let's start with 1 implies 12. Assume A is invertible. And then A transpose times A inverse transpose equals A inverse A transpose. Remember, if you take the product of these two matrices, notice that they're reversed from these two. Well, this is equal to I sub n transpose, and the identity matrix, if you transpose it, it's still the identity matrix because none of the diagonal elements are changed and everything else was 0 anyways, so that doesn't make a difference. Nope, I actually missed something here. To prove that it's invertible, I need to show it's true on the other side as well. So here then I will have A times A inverse transpose, which equals IN transpose, which of course equals IN. So therefore, A transpose is invertible. Now let's do 12 implies 1. Assume A transpose is invertible. Now I don't know the structure of it, but I can say that then there is a matrix. Oh, I don't know, let's call it, I want to use a different letter than before, B, such that A transpose B equals B A transpose equals the identity matrix. But then A transpose B equals B transpose A. Notice how I reverse them, and B transpose transpose is the same as it was with itself as before. Now I know on the left that this is I sub n. Now I know that the identity matrix is the same as the identity matrix transpose. So IN transpose will equal B transpose A transpose transpose. That's just B transpose A, and IN transpose is just IN. On the other hand, I can reverse this then. IN equals B A transpose, which equals A B transpose transpose, right? So IN transpose equals A B transpose transpose transpose. So IN equals A BT. So I have that A has a two-sided inverse, so therefore A is invertible. And thus we have 1 through 12 are all equivalent. Another theorem. let A and B be square matrices. If AB equals IN, then A and B are both invertible, and A equals B inverse, B equals A inverse. Proof. If AB equals IN, then A has a right inverse, which implies A is invertible by the invertible matrix theorem. I don't remember what number that was, but one of the things was that if you had a right inverse, then A was invertible. Another one is that if you had a left inverse, A was invertible. But I'm going to use that here also. AB equals IN implies that B has a left inverse. So B is invertible by the invertible matrix theorem. Next we have this, B inverse equals IN times B inverse, and IN was equal to AB, and I'll regroup A times B inverse equals A. So B inverse is equal to A. You show that A inverse equals B using almost identical reasoning as I just did. Let's do an example. Is -4, 6, 6, -9 invertible? Well, let's take a look. If I take 1.5 times -4, 6, that'll equal 6, -9. So when I put it in another format, you might recognize it. In that format, you can see that the columns are not linearly independent. So the matrix is not invertible by the invertible matrix theorem. Most of these examples are going to go straight from the theorem or that thing that I just proved after it. Here's the matrix I'm going to give you. -7, 3, 2, 0, 0, 0, 4, -1, 9, -1, 9, invertible. Well, here you can do the following. I can do 0 times negative 732 plus 1 times 0, 0, 0 plus 0 times 4, negative 1 to 9. And hopefully you can see that that's the 0 vector. This implies that the columns are not linearly independent. So the matrix is not invertible by the invertible matrix theorem. And you might have recalled earlier in the semester there was a statement that said any set of vectors that included the 0 vector was automatically not linearly independent, and that's because you could do this kind of stuff. You could zero out the non-zero vectors and then put your one and only one non-zero scalar attached to the 0 vector, and you end up getting a linear combination that adds up to 0. Is, let me put another 3 by 3 up here, 1, 0, negative 3, negative 5, 3, 6, negative 4, 4, 0, invertible. This one's a little bit harder to see right off the bat. So what I'm going to do is I'm going to do 3R1 plus R3. And I'll get 1, 0, 0 there. And let's see, negative 15 plus 6 is negative 9. And then I have negative 12 plus 0 is negative 12. Then I can do 3R2 plus R3. And I think right now I can stop. If you look here, I have a pivot here and I have a pivot here. Only 2 pivots. But we need 3. So therefore, the matrix is not invertible. I should say we need 3 pivots by the invertible matrix there. Remember, a matrix was invertible if it had n pivot positions. We only have 2 here and we need 3 of them. Is, here I think I'm going to do a 4 by 4, 1, 0, 0, 0, 3, 5, 0, 0, 7, 9, 2, 0, 4, 6, 8, 0. Is this invertible? Well, let's take a look. Same deal as before. I have a pivot here, a pivot here, a pivot here. Only 3 pivots. Implies the matrix is not invertible, as we'd need 4 pivots to ensure invertibility. And once again, this is by the invertible matrix theorem. Show that if A, B are n by n matrices where AB is invertible, then A is invertible. So if AB is invertible, notice we're not saying that both A and B are invertible, just the product is invertible. So if AB is invertible, then there is a matrix D such that AB times D equals IN. But I can regroup. This implies that A has a right inverse. So A is invertible by the invertible matrix theorem. Now, you should also be able to prove that B is also invertible, and you should be able to come up with a left inverse for it. Let me review something here a little bit. Do you remember that a function, let's just go and do the real numbers to remind you, a function f from R to R is invertible if there is a function g such that f circle g of x equals x for all x in the domain of G, and similarly G circle F of x was equal to x for all x in the domain of F. And you knew this. F circle G, for example, of x is no different than F of G of x. And similarly, G circle F of x is the same as G of F of x. So we're going to come up with an inverse for linear transformations based on this definition here. So let me go ahead and do that. So if, let me mark this off, if T is a linear transformation from Rn to Rn, then T has an inverse, for now we'll call it S, from Rn to Rn, if S is a linear transformation and T circle S of x equals x for all x in Rn, and S circle T of x equals x for all x in Rn. Now it's slightly different here because the domain for each of these functions is all of Rn, so we don't have to worry about the domain having anything to do with these. So these equations are true for all x in Rn because these functions are defined for all x in Rn. In this case, we write T inverse equals S. A theorem. Let T from Rn to Rn be a linear transformation. And let A be the standard matrix for T. So remember, that means that T of x is equal to A times x. T is invertible if and only if A is an invertible matrix. In fact, T inverse of x will equal A inverse x. So it's easy to get a formula for T inverse. Let's go ahead and do the proof. Let me go first in the forward direction and assume T is invertible. Then there is a linear transformation S from Rn into Rn with T circle S of x equal to x for all x in Rn. Well, this is no different than T of S of x equals x. But then remember, T of x equals AX. So that means over here I'll have an x, and then I'll have an A times S of x. Like so. Since this is true for all x in Rn, we see that T is onto. In other words, the mapping x to AX is onto. Thus, A is invertible by the invertible matrix theorem. Now let's go the other direction. Here, assume that A is an invertible matrix. Let S of x equal A inverse times X. We know that S is a linear transformation. That was proven way long time ago. Also, let's take a look at what we have here. If I try to do T circle S of X, that's T of S of X, which is A of S of X, which is A times A inverse times X. Regroup A inverse X equals IN X equals I sub n. And you go the other way and you're not going to have much difficulty trying to do this. Show that this equals X as well. You show this using almost identical steps that I did. And then we'll have that S and T are inverses of each other. By the way, the S of X in the theorem is unique. Suppose T circle V of X equals V circle T of X, and that equals X, just like T circle S. Then what we have is V of X. That'll equal V of T circle S of X. Remember that X was equal to T circle S. And then this is then going to be equal to V of T of S of X, like so. But then that is V circle T of S of X. But V circle T is the identity function. That means whatever's in the parentheses is what it equals. And so we see that V and S are the same thing. So as I mentioned, that S is unique. Let T from R2 into R2 be given by T of X1, X2 equals 6x1 minus 8x2, negative 5x1 plus 7x2. And so let me just do one more thing here. I'm going to write it in matrix notation. Like that. The matrix is invertible since when you take the AD minus BC, remember this AD minus BC? That was when the matrices were of this form, A, B, C, D. Well, that's what I'm going to do here. AD minus BC, I'm going to have 6 times 7 minus negative 5 times negative 8. And that is equal to 2, which is not equal to 0. So the matrix is invertible since that thing does not equal 0. The inverse of the matrix is, let me write it out in some detail for you. Remember, the inverse of these 2 by 2s is 1 over that AD minus BC. And then what you did with these special matrices is you swapped the first and the last numbers, and then you negated the other numbers, like that. And so this is 1/2 times 7, 8, 5, 6. So this implies that my inverse function is given by the inverse matrix times x. Suppose T and U from Rn to Rn are linear transformations. Such that T of U of x equals x for all x in Rn. Let AT be the standard matrix for T, and let A sub U be the standard matrix for U. Since T of U of x equals x for all x in Rn, we have let me put my T down there, and that equals AT times AUX, which equals AT AUX, which equals x. I meant to say for all x in Rn. I keep reminding you of that. So AT AUX equals x for all x in Rn. Well, then we have AT AU times EI equals EI for all elementary matrices. Do I want to call them that? Let's call them elementary vectors. EI. Remember, E1 has a 1 in the first slot and zeros everywhere else. E2 has a 1 in the second spot with zeros everywhere else. You remember what these things are. Well, what I can do then is I can take and create a matrix here. AT, AU, E1, dot, dot, dot. And I should probably do this. AT, AU times En. And of course, that equals E1, dot, 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 up to En. But I can factor out then the AT, AU times E1, dot, 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 En. And that equals E1, dot, 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 En. And then I have AT, AU. I keep forgetting my things around that. In equals In, which just means that AT, AU equals IN. Well, then AT has a right inverse and AU has a left inverse, so this implies that AT and AU are invertible by the invertible matrix theorem. Also, by the problem we did a little bit ago, we have AT equals AU inverse and AU equals AT inverse. Not only that, if they're inverses of each other, AT and AU, then we also know that AT-AU equals AU-AT. All right, then what we can do is take a look at our original mapping, T of U of X. That was equal to A times U of X, which is A times, well, that was AT, wasn't it? AT, AU X, which equals AT-AU times X. Now let me turn them around. AU-AT times X, which equals AU times AT-X, which equals AU times T of X, which equals U of T of X. So what we have then is that U circle T equals T circle U. So these functions commute. Let T from Rn to Rn be an invertible linear transformation. Suppose S and U from Rn to Rn are merely functions, but S of T of X equals U of T of X equals X for all X in Rn. Show that S of V equals U of V for all V in Rn. Basically, just show the functions S and U are equal to each other. Proof. Let V be in Rn. So I'll have that hanging around while we're doing it. Since T is invertible, its standard matrix is invertible. Okay, so we know that already. Then we know that the mapping X goes to AX is 1 to 1 and onto. So T is onto. That's what I need to know for what I'm going to do. Let W be in Rn such that T of W equals the given B. Since T is onto, I can find such a vector W for which that happens. But then S of V equals S of T of W, because T of W equals V. But I know that that is equal to W. U of V equals U of T of W equals W. So I have S of V equals W equals U of V, and that finishes the proof.